All right, today we're going to go deep, like way, way deep, right down into the guts of a computer processor. We're going to pull back the curtain and see exactly how a computer tackles a multiplication problem that seems totally simple to us, but for a machine, well, it takes a very specific, very clever tool to get the job done right.
Okay, so here's our game plan. First, we'll talk about why big numbers are even a problem for computers in the first place. Then we'll meet our hero for the day, a special instruction called SMUL. After that, we need to cover a really cool trick computers use for negative numbers. Then we'll put all those pieces together to actually solve the multiplication. And finally, we'll see exactly how the computer stores that final answer.
So let's start with the core challenge here. You got to remember that computers think in fixed-sized boxes, right? These things are called registers. But what happens when the math you're doing creates an answer that's just too big for the box?
Yeah, exactly this. It's like, imagine you have two boxes, and they can each hold 32 of something. You do some math with what's inside, and suddenly the result needs a much bigger box, a 64-item box. If you just try to jam that big result into another standard 32-bit box, you literally lose half the information. It just gets chopped off and thrown away. That's a huge problem.
So, how do they solve this? Well, lucky for us, the smart folks who design ARM processors came up with a specialized tool in their toolbox just for this exact big baby situation.
And here it is. It's called SMUL, which is short for Signed Multiply Long. Its entire reason for existing is to multiply two 32-bit numbers. But, and this is the whole magic trick, it doesn't try to force that huge 64-bit answer into one tiny box. Instead, it cleverly uses two separate registers to catch the entire thing, making sure not a single bit gets lost.
You know, the cool thing is you can see the whole story right in the instruction itself. R and M, those are your two starting numbers, your inputs. The instruction does the math, and then it takes the result and splits it. It puts the lower 32 bits into RD low and the upper 32 bits into RD high. It's like a perfect blueprint for how to solve the problem.
Okay, but hold on. Before we can see SMUL do its thing, there's one more piece of the puzzle we got to understand. It's this brilliant little system that all computers use to handle negative numbers. It's called 2's complement. Yeah, think about that. This isn't just some random method. It's an incredibly efficient piece of engineering. By representing negative numbers this way, the processor doesn't need one set of circuits for adding and a completely different set for subtracting. It can use the exact same hardware for both, which makes it way simpler and faster. Pretty smart, huh? So let's walk through it real quick. It's actually just 3 simple steps. To get to -20, you first start with the binary for +20. Easy enough. Then, step 2, you just invert everything. Every 0 becomes a 1, and every 1 becomes a 0. And finally, you just add 1 to that result. And boom, that final binary number, that's how a computer sees -20.
All right, we have all our tools on the table now. We get the problem, we've met the SMUL instruction, and we know the 2's complement trick. So let's put it all together and actually execute our instruction. Here's the exact scenario. We're telling the processor, hey, run the SMULL command. We're telling it to take the number sitting in register R5, which is 100, and multiply it by the number in register R6, which is -20. And we're saying whatever the answer is, put it in registers R7 and R8. First, let's just do the math like a normal person in our heads. 100 times -20 is, of course, -2000. So this is our target. This is the answer the processor needs to get to. It just has to do it using nothing but ones and zeros. So what does the CPU do first? It preps its inputs. It takes that 100 from register R5 and converts it to its 32-bit binary form. Then it takes the -20 from R6 and uses that 3-step 2's complement process we just talked about to get its binary version. Now for the actual multiplication. The processor does the math and gets the result, -2000. But, and this is super important, it doesn't represent this as a small number. It calculates it as a full, complete 64-bit number to make absolutely sure no data gets cut off. And how does it get the 64-bit binary for -2000? Well, you probably guessed it. It's that same 2's complement process all over again. It starts with +2000, inverts all 64 of the bits, and then just adds 1. Same exact logic, just on a bigger scale. And there it is. That's what -2000 actually looks like inside the processor's calculation unit. It's this long 64-bit string. And see all those ones at the beginning?
That's the classic signature of a negative number in 2's complement.
So the math is done. The calculation is complete. But the processor's job isn't over. Now comes the most important part, the step where the SML instruction really earns its keep. How does it store this giant number so the program can actually use it?
It just chops it right down the middle, perfectly. The top half, the upper 32 bits, get placed into our high register, R8. And the bottom half, the lower 32 bits, go into our low register, R7. And just like that, problem solved. The entire 64-bit answer is stored safely with nothing lost. Now, if you were a programmer looking at this with a debugger tool, you probably wouldn't see all those ones and zeros. You'd see something like this. These are hexadecimal values. You can just think of hexadecimal as a convenient shorthand for programmers. It's a much cleaner, more compact way for us humans to read those long, messy binary numbers. So, why does any of this matter? Because these tiny, almost invisible, low-level instructions, they're the microscopic engines that are running everything. Every video game you play, every complex scientific model. It's all built on top of fundamental operations just like this one. Understanding this stuff gives you a real appreciation for the sheer elegance and power humming away inside your devices millions of times a second. And that kind of leaves you with one final thought, doesn't it? We just saw how much clever engineering has to go into something as seemingly basic as multiplication. With its special instructions and tricks for negative numbers, it really makes you wonder, what kind of wizardry is going on inside that chip to handle something even harder, like division? Thanks for digging into this with us.